Hello and welcome to Calculus 2 here at Cañada College. My name is Lapuz. In this video we'll be looking at checkpoint 6.9 from section 6.2. It says to integrate this power series, and we have the function ln of 1 plus x, which is equal to the series n goes from 1 to infinity of -1 raised to the n plus first power times x to the n over n. So this looks like it's an alternating series, and we're going to want to do some term-by-term integrating. The nice thing about series is that when you take the derivative of or integral of a series, because you're adding these things, you would be integrating or differentiating term by term. And so that is essentially the same thing as coming up with the antiderivative or the integral of just whatever is inside the series, because those are each of the terms kind of taken on by different values of n. Okay, so let's start off. Let me rewrite this equation. Ln of 1 plus x equals this series going from 1 to infinity of -1 to the n plus 1 times x to the n over n. All right, now let's integrate both sides. And if we integrate both sides with the dx, and we'll see that that the integral of ln of 1 plus x dx, well, let's not worry about that. This would be some term-by-term integrating. And what that tells us is that we know that the integral of a sum is a sum of the integral. And so let's just take the sum of each of these integrals of -1 to the n plus 1 times x to the n over n dx. Okay, so this is the part that we're really working on right here, finding this antiderivative. Let's take that off to the side here. Integral of -1 to the n plus 1 times x to the n over n dx. And then we'll put it back into the sum figure here. Now this -1 to the n plus 1 is a constant, and as a matter of fact the n is also a constant, so we can take those out of our antiderivative. So all we have is this integral of x to the n dx. Alright, let's keep that constant hanging around. -1 to the n plus 1 over n. Let's take the antiderivative of this now. This will be equal to x to the n plus 1 divided by n plus 1. That's the antiderivative. Now technically there's a plus c, so we could put the plus c there and deal with that later, separately, whatever. So I think we have our information. Let's go ahead and combine. Let's not worry about the plus c. Let's go ahead and combine this. So it's still going to be an alternating series. This is going to be the series n goes from 1 to infinity of, and I think we're going to worry a little bit about this starting point 1, but we'll deal with that in a minute. We have -1 to the n plus first power over n, and this is an n plus 1 in the denominator as well, so let's attach that, and then we have x to the n plus 1. All right. We can do a shift in the index, and just so we can make this look like x to the n. So let's imagine subtracting out a 1 from the n, and then we'll add 1 from the end here. Okay, so the little trick is to add 1 to the starting point, and then we're going to take away 1 from the end. So it's going to be -1 raised to the m minus 1 plus 1, so that's just going to be to the nth power. And then wherever we see an n, we're going to replace it with n minus 1. And n minus 1 plus 1 is just going to be a regular n. And then this would be x to the nth power. Okay. So this is going to be your new series for this antiderivative. Now you can take the antiderivative yourself if you want to see what that new function is. But sometimes these antiderivatives don't have closed forms. This one would, because we know the antiderivative ln x. But in general, there might not be a closed form for the antiderivative, so you're just going to have to rely on the series to produce it. Okay, in this case, I think this is going to be our result, and that's it. All right, I hope that helps. Good luck.